Look up at the night sky, past the familiar glow of stars, beyond the swirling arms of our galaxy, and try to imagine the vast emptiness between worlds. It's a silent, frozen ocean stretching light years in every direction, where temperatures plunge to hundreds of degrees below zero, and radiation slices through the darkness like an invisible storm. Yet hidden in this unforgiving void, there might be something extraordinary, tiny vessels carrying the very ingredients of life itself. What if comets, those icy wanderers streaking across our skies, aren't just cosmic debris but interstellar messengers? What if billions of years ago, one of them crashed into our young planet, delivering the seeds that sparked everything we know? This isn't science fiction. It's a real scientific theory called Panspermia, the idea that life could travel between stars, hitching rides on comets or asteroids, spreading like a cosmic contagion. Think about it. Comets are frozen time capsules packed with organic molecules, water, and even amino acids, the building blocks of proteins. When they collide with planets, they don't just leave craters, they might deposit the raw materials for biology. And here's the truly mind-blowing part. If life could hop from one world to another, then Earth might not be the only cradle of life. We could be part of a much larger, interconnected story, a chain of existence spanning entire galaxies. So let's dive into the evidence. From ancient Martian meteorites carrying mysterious structures to the discovery of complex organic compounds in distant nebulae, science is uncovering clues that challenge our understanding of life's origins. Could comets really be the gardeners of the universe, scattering life wherever they go? And if so, what does that mean for our place in the cosmos? Buckle up, because we're about to explore one of the most thrilling mysteries in science. Are we all, in some way, children of the stars? The idea that life might have arrived from the stars isn't as new as you might think. Over 2,000 years ago, Greek philosophers like Anaxagoras speculated about seeds of life drifting through space, tiny sparks of existence scattered across the cosmos, waiting to take root wherever conditions allowed. But for centuries, this remained little more than poetic speculation. Fast forward to the 19th century, when scientists like Svante Arrhenius, the Nobel Prize-winning chemist, revived the idea with his theory of radiopanspermia, proposing that microscopic spores could be pushed through space by the pressure of starlight, riding beams of light like cosmic dust. Then came Fred Hoyle and Chandra Wickramasinghe, two bold thinkers who turned panspermia into a serious scientific debate. In the 1970s and 80s, they challenged the mainstream view that life emerged solely from Earth's primordial soup. Hoyle, an astrophysicist famous for coining the term Big Bang, and Wickramasinghe, a mathematician and astronomer, argued that comets weren't just icy rocks, they were carriers of complex organic molecules. They even suggested that interstellar dust contained biological material, an idea met with skepticism at the time. But as telescopes and space probes grew more advanced, something remarkable happened. Science started catching up with their vision. What makes panspermia so provocative isn't just the science, it's how it flips our understanding of life's origins on its head. For decades, the dominant theory was abiogenesis. Life arose spontaneously on Earth from non-living chemicals, a slow simmer of chemistry in warm tidal pools or deep-sea vents. But panspermia throws open a much bigger door. What if life didn't begin here at all? What if, instead of a single spark on one lucky planet, life is a cosmic inevitability, hopping between worlds whenever the chance arises? Think of it like this: if life on Earth was planted by a comet, then we might be part of a grander cycle, one that could have spread to countless other planets. That's why panspermia isn't just about the past, it reshapes how we search for life today. If microbes can survive the harshness of space, then Mars, Europa, or even distant exoplanets might not need to cook up life from scratch. They could have been seeded just like us. Of course, not everyone agrees. critics argue that space is too hostile radiation, extreme cold, and the vacuum itself should shred delicate organic molecules. Yet recent discoveries keep breathing new life into the theory. Meteorites like the famous Martian rock LH-84001 have revealed tiny structures that some scientists believe could be fossilized microbes. Meanwhile, probes like Rosetta found amino acids on Comet 67P, exactly the kind of building blocks Hoyle and Wickramassing predicted. So while Panspermia remains controversial, it's no longer fringe. It's a compelling counterpoint to Earth-centric theories, forcing us to ask, if comets delivered life here, where else might they have dropped their precious cargo? Comets aren't just dazzling streaks of light in our night sky, they're cosmic icebergs, drifting through space with secrets locked deep inside their frozen cores. Picture a mountain of ice and rock, some as large as cities, hurtling through the void at speeds that defy imagination. But what makes them so special isn't just their spectacle, it's what they carry. These wandering giants are packed with water ice, frozen gases like methane and ammonia, and most intriguingly, complex organic molecules. In many ways, they're natural deep-freeze vaults, preserving the raw ingredients of life across the unimaginable cold and emptiness of space. Take a closer look at a comet's structure and you'll find three key layers. The nucleus, its solid heart, is a mix of ice and dust, a dirty snowball as scientists often describe it. Surrounding that is the coma, a hazy cloud of gas and dust that forms when the sun's heat vaporizes the comet's surface. And stretching millions of miles behind it, the iconic tail, a shimmering trail of particles pushed away by solar winds. But the real magic happens in that icy nucleus. Locked within are amino acids, the same molecules that form proteins in every living thing on Earth. There's glycine, the simplest amino acid, detected on Comet 67P by the Rosetta mission. There's ethanol and even sugars like ribose, critical for the backbone of DNA. These aren't random contaminants, they're fundamental pieces of life's puzzle, surviving in the deep freeze of space for billions of years. Why does this matter? Because comets are more than just frozen relics, they're time capsules from the birth of our solar system. When the planets were still forming, comets were the delivery trucks of the cosmos, ferrying water and organic material across the young solar system. Earth, scorched and barren in its early days, might have owed its oceans to countless comet impacts. But here's the twist: if comets could bring water, why not the building blocks of life too? Laboratory experiments show that the icy vacuum of space can act like a chemistry lab, with radiation-sparking reactions that turn simple molecules into complex ones. Over millennia, these molecules could accumulate in comets, shielded from harsh radiation by layers of ice. And let's not forget durability. Space's brutal cosmic rays, extreme temperatures, and the vacuum itself should, in theory, tear apart fragile organic compounds. Yet comets defy this. Their icy shells act like insulation, protecting the delicate cargo inside. Some microbes on Earth, like the ultra-hardy tardigrades, can survive the vacuum of space in a dormant state. If life's ingredients can endure such extremes, why couldn't they hitch a ride on a comet, drifting between stars until they find a welcoming planet? This isn't just speculation, the evidence keeps mounting. In 2020, researchers found phosphorus, a key element for DNA and cell membranes, in the coma of Comet 67P. Then there's the discovery of polycyclic aromatic hydrocarbons, complex organic compounds, in the tails of comets. Each finding paints a clearer picture: comets aren't sterile. They're rich with the very materials life needs to begin. So the next time you see a comet blazing across the sky, remember, it might be more than a beautiful spectacle. It could be a messenger from the distant past, carrying whispers of how life began, not just here, but perhaps across the cosmos. And if that's true, then every one of us, every tree, every creature, might owe our existence to these icy wanderers. The universe, it seems, has a way of spreading its secrets one comet at a time. Imagine a creature so tough it can survive the vacuum of space, blistering radiation, and temperatures near absolute zero, then wake up unscathed, ready to carry on as if nothing happened. Meet the tardigrade, also known as the water bear, a microscopic 8-legged animal that's rewriting the rules of where life can exist. These tiny titans, no bigger than a grain of sand, are nature's ultimate survivalists, and they might hold the key to understanding how life could journey between the stars. Tardigrades aren't alone in their resilience. Across Earth's most hostile environments, from boiling hydrothermal vents to the frozen deserts of Antarctica, organisms known as extremophiles thrive where nothing else can. Some bacteria, like Deinococcus radiodurans, can withstand radiation doses thousands of times stronger than what would kill a human. Others, like certain archaea, flourish in acidic pools or deep underground, cut off from sunlight and oxygen. These organisms don't just endure extreme conditions, they've evolved to depend on them, and that raises a tantalizing question. If life can adapt to Earth's harshest corners, why not the even greater extremes of space? Scientists have put this idea to the test in ways that sound like science fiction. In 2007, the European Space Agency launched tardigrades into orbit aboard the Photon M3 mission, exposing them to the raw vacuum and solar radiation of space for 10 days. The results, many not only survived, they later reproduced as if their cosmic vacation was just a minor inconvenience. Similar experiments with bacteria and lichens have shown that certain species can endure years attached to the outside of the International Space Station, shielded only by thin layers of rock or synthetic material. These aren't just lab curiosities, they're proof that life, once it exists, is far hardier than we ever imagined. But how do they do it? Tardigrades and other extremophiles have biochemical tricks that border on the miraculous. When conditions turn deadly, tardigrades enter a state called cryptobiosis, essentially shutting down their metabolism and replacing the water in their cells with a protective sugar called trehalose. In this dried-out ton state, they can wait decades, maybe even centuries, for water to return. Radiation-resistant bacteria, meanwhile, pack their DNA with repair enzymes that stitch broken strands back together at astonishing speeds. These adaptations aren't just accidents, they're blueprints for how life might endure the unimaginable journey through interstellar space. Now picture this: a comet laden with organic molecules plows through a cloud of microbial spores drifting between stars. The spores, hardened by millennia of exposure, latch onto the comet's icy surface. As it travels, the comet's frozen shell shields them from radiation, while the vacuum keeps them in suspended animation. Millions of years later, the comet collides with a young, watery planet, and the spores awaken in a new home. It's not fantasy. Experiments like the EXPOSE missions, where scientists mounted biological samples to the exterior of the ISS, have shown that some organisms can survive this exact scenario if shielded by just a few millimeters of rock or ice. Critics argue that space's vast timescales and radiation levels would still doom any hitchhiking life, but extremophiles force us to reconsider. If tardigrades can survive days of direct solar exposure, what might endure over millennia tucked safely inside a comet's icy interior? If bacteria can repair radiation damage in hours, how much could they withstand with the right protection? The line between impossible and improbable grows thinner with every new discovery. This isn't just about microbes clinging to comets, it's about redefining life's potential. If organisms can survive space's brutality, then Panspermia isn't just poetic speculation. It's a testable, plausible pathway for life to spread, and that changes everything. Suddenly, the universe feels less empty, more connected. A place where life, once sparked, might find a way to endure and spread against all odds. We might not be alone. We might, in fact, be part of a much larger story, one written in the DNA of creatures so resilient they've turned the cosmos itself into a highway. In 2014, humanity took its closest look yet at a comet, not from afar through telescopes, but up close with a robot named Rosetta. This ambitious mission by the European Space Agency didn't just snap pictures. It chased down comet 67P Churyumov-Gerasimenko, matching its speed, orbiting it for 2 years, and even deploying a lander to touch its surface. What Rosetta found there wasn't just rock and ice. It was a treasure chest of clues, rewriting our understanding of how life's ingredients might spread across the cosmos. One of the most jaw-dropping discoveries, glycine, the simplest amino acid, a fundamental building block of proteins. This wasn't contamination from Earth. Rosetta's instruments detected it drifting in the comet's faint atmosphere, clear evidence that these molecules form in deep space. But glycine wasn't alone. The probe also found phosphorus, a critical element for DNA and cell membranes, hinting that comets could deliver not just the basics of life, but the very framework it needs to assemble itself. Picture this as Rosetta circled 67P. Its sensors analyzed the comet's coma, the hazy cloud of gas and dust surrounding it. Hidden in that cloud were alcohols, sugars, and even formaldehyde, all molecules that, under the right conditions, can react to form more complex organic compounds. These weren't random chemicals, they were pieces of a puzzle, showing how the universe might cook up life's precursors long before they reach a planet. And then there's the water. Comet 67P's ice didn't match Earth's oceans perfectly, but it carried a striking ratio of heavy hydrogen, suggesting that at least some of our planet's water, and possibly the organics dissolved in it, could have arrived via comet impacts. Imagine a young Earth, barren and scorching, bombarded by icy wanderers that didn't just bring water, but the chemical seeds of biology itself. Rosetta's findings didn't just support Panspermia. They painted comets as cosmic chemists, crafting life's ingredients in the frozen void. Scientists had long suspected space could synthesize simple organics, but discovering them intact on a comet, that was like finding a fully stocked pantry drifting between the stars. Even more compelling, the molecules weren't scattered randomly. They clustered in the comet's darker, colder regions, shielded from solar radiation. This suggested a protective mechanism, a way for fragile compounds to survive their violent journey through space. Critics had argued that space radiation would shatter complex molecules before they could reach a planet. Rosetta's data countered that. The comet's surface was a dynamic laboratory, with ultraviolet light and cosmic rays actually triggering reactions that built more complex compounds, not just destroyed them. It's as if the universe conspires to create life, using comets as both factories and delivery trucks. The mission's climax came when Rosetta's lander, Philae, bounced across the comet's surface, a messy landing but one that yielded gold. Its drill revealed organic, rich material beneath the crust, further proof that the building blocks of life aren't rare flukes but cosmic inevitabilities. Even in failure, Philae triumphed. Its struggle to power up in the shadows mirrored life's own tenacity, clinging against the odds. Rosetta didn't just study a comet, it gave us a new perspective on our origins. If 67P, a random visitor from the Kuiper belt, carried such riches, how many other comets might be out there ferrying life's blueprints between the stars? The mission's legacy isn't just data, it's a paradigm shift. We're no longer just earthbound creatures wondering if life exists elsewhere. We're part of a universe that seems determined to spread it, one icy traveler at a time. Before Rosetta, there was Deep Impact, NASA's bold 2005 mission that didn't just observe a comet from a distance, but literally punched a hole in one to see what lay beneath. The target was Tempel 1, a city-sized chunk of ice and dust orbiting the Sun, and the plan was audacious. A washing machine-sized probe, packed with sensors and cameras, would slam into the comet at 23,000 miles per hour, blasting open a crater and revealing secrets buried for billions of years. The result, a scientific goldmine that challenged everything we thought we knew about comets and their role in life's origins. As the impactor struck, telescopes and spacecraft around the solar system trained their instruments on the explosion of debris. What they found stunned researchers. Instead of just simple ices and dust, Tempel 1's interior held a cocktail of complex hydrocarbons, molecules with structures eerily similar to those found in crude oil and coal. But here's the twist: these weren't the product of ancient forests or decaying life. They'd formed in the frozen darkness of space without biology's help. Even more striking was the discovery of clay-like silicates, minerals that on Earth act as catalysts, speeding up chemical reactions that could turn simple organics into more complex ones. In essence, Tempel 1 wasn't just carrying life's ingredients, it was carrying the very tools needed to assemble them. The mission also shattered the myth of comets as uniform, dirty snowballs. Deep Impact revealed a layered interior with regions of porous, fluffy material and others dense as packed snow. This structure suggested comets weren't just passive lumps of ice but dynamic objects, shaped by heat and cosmic radiation over eons. Some scientists now think these layers could act as protective zones, shielding delicate organic molecules from destruction while allowing chemical reactions to simmer slowly in the cold. Perhaps the most tantalizing clue came from the mission's spectral data. Hidden in the plume of ejected material were compounds like polycyclic aromatic hydrocarbons (PHs) for short, complex carbon-based molecules found everywhere from interstellar clouds to the charred crust of your morning toast. On Earth, PHs are often byproducts of combustion, but in space they form naturally under the cold, diffuse conditions of molecular clouds. Their presence on Tempel 1 hinted that the universe might be quietly assembling life's building blocks in the most unexpected places. Critics had argued that comets were too primitive to play a role in life's origins, but Deep Impact painted a different picture. Here was a body rich in both raw materials and the means to organize them, a chemical factory drifting between the stars. And if Tempel 1 had these resources, how many other comets might be out there carrying the same probiotic toolkit? The implications ripple outward. If clays and hydrocarbons were delivered to early Earth by comet impacts, they might have jump-started the chemistry that led to RNA, proteins, and eventually cells. The mission's legacy goes beyond a single crater. It forced scientists to rethink comets not as relics but as active participants in the story of life. Tempel 1 showed us that the line between non-living and living might blur in the icy depths of space, where chemistry quietly arranges itself into ever more complex patterns. And if that's true, then every comet streaking through our solar system isn't just a spectacle, it's a potential chapter in the biography of life itself, written in molecules that might one day awaken on a distant, waiting world. In October 2017, astronomers spotted something unprecedented, a strange, elongated object hurtling through our solar system at blistering speed. It wasn't a comet, it wasn't an asteroid, and it wasn't from around here. Named Oumuamua, Hawaiian for scout or messenger, this interstellar visitor became one of the most debated cosmic mysteries of our time. Tumbling through space like a rogue cigar, its peculiar shape and unexpected behavior defied easy explanation. But the real shock came when scientists realized it wasn't just coasting, it was accelerating as if pushed by some unseen force. Theories erupted. Could Oumuamua's speed boost have come from outgassing, the same process that gives comets their shimmering tails? Normally, when sunlight heats a comet's icy surface, it releases gas and dust, creating a visible trail. But Oumuamua showed no coma, no tail, no obvious signs of sublimation. If it was outgassing, it was doing so invisibly, like a ghost comet. Some researchers proposed that its ices might have been rich in hydrogen or nitrogen, gases that wouldn't reflect light like water vapor but could still provide thrust. Others pointed to its bizarre shape, a flattened pancake or needle-like rod, as evidence of erosion from eons of cosmic weathering, leaving behind an exotic, hardened crust. Then came the wilder possibilities. Harvard astrophysicist Avi Loeb famously suggested Oumuamua might not be natural at all. Could its acceleration have been caused by a solar sail, a thin, reflective sheet propelled by starlight like a ship's sail catching the wind? The idea sparked fierce debate, with critics arguing that extraordinary claims require extraordinary evidence. But Loeb stood firm, pointing out that science should always leave room for the unexpected. After all, if we only look for what we already know, we might miss the truly revolutionary. Here's where things get even stranger. Oumuamua's trajectory suggested it came from the direction of Vega, a star 25 light-years away. But by the time it reached us, Vega had moved, meaning Oumuamua might have wandered the galaxy for millions, even billions of years before stumbling into our neighborhood. Imagine that, a silent traveler, adrift between stars since before Earth formed, carrying secrets we may never fully unravel. Visualizing Oumuamua's journey takes us into the realm of speculation. Picture a dark, tumbling slab, its surface scarred by micrometeorites and cosmic rays, spinning erratically as it streaks past the sun. Sunlight glints off metallic patches, not ice but something more resilient. Deep inside, trapped gases slowly warm, hissing through cracks in its crust like steam from a kettle, nudging it off a purely gravitational path. Or perhaps, as some simulations suggest, it's a fragment of a shattered super-Earth, blasted into space by an ancient cataclysm, its dense, layered interior hiding clues to planetary formation we've never seen before. The truth is, we may never know for certain. Oumuamua is now beyond the reach of our telescopes, speeding toward the outer solar system. But its legacy lingers, a reminder that the cosmos is far stranger than we imagine. Whether it was a peculiar comet, a shard of a distant world, or something even more extraordinary, Oumuamua challenges us to rethink what's possible. In a universe where comets might ferry life between stars, who's to say the next interstellar visitor won't rewrite the rules all over again? Until then, we're left with a tantalizing thought. If Oumuamua was the scout, what or who might follow? Picture this: 4.5 billion years ago, Earth is a newborn world, molten, violent, and utterly inhospitable. Volcanoes erupt across its surface, spewing lava into an atmosphere thick with toxic gases. No oceans, no continents, just a hellish landscape bombarded by asteroids and comets in a chaotic dance called the Late Heavy Bombardment. Then, from the darkness comes a visitor, a comet the size of a mountain, screaming through the sky at 40,000 miles per hour. When it strikes, the impact is apocalyptic. Rock vaporizes instantly. Tsunamis of molten stone ripple across the globe. But buried in that chaos is something extraordinary: the comet's hidden cargo, a payload of frozen water and organic molecules that might just change everything. This isn't just destruction, it's delivery. As the comet's icy core vaporizes on impact, water molecules spread through the atmosphere, condensing into rain that falls for centuries, filling low-lying basins to form Earth's first seas. Meanwhile, the heat of the impact actually protects some of the comet's fragile organic material. Deep beneath the surface, shielded from the worst of the blast, amino acids and sugars survive, mixing with minerals and hydrothermal vents to create a primordial soup. Scientists call this the impact frustration paradox, the idea that while colossal collisions can sterilize a planet, they might also provide the raw ingredients for life to begin anew. To understand how this works, let's zoom in on the chemistry. When a comet strikes, the sudden pressure and heat create shock waves that trigger reactions between simple molecules. Experiments at NASA Ames Research Center show that comet-like ices, when subjected to impact conditions, generate nucleobases, the very letters of our genetic code. Imagine a cosmic pressure cooker. One moment you have frozen ammonia, methanol, and water. The next, a violent collision rearranges them into compounds like adenine and guanine, essential for DNA and RNA. Even the clay minerals found in comet dust play a role. Their layered structures act like tiny factories, concentrating organic molecules and catalyzing reactions that might have led to the first self-replicating molecules. But water is only half the story. Comets also deliver rare elements critical for life. Take phosphorus, for example, a key component of cell membranes and energy-carrying molecules like ATP. On early Earth, most phosphorus was locked up in insoluble minerals, but comets carry it in more reactive forms like phosphine, a gift that could have jump-started metabolism. And then there's deuterium, a heavy hydrogen isotope found in comet water. Earth's oceans have a specific deuterium signature, and surprisingly, some comets match it, suggesting they contributed not just water, but the precise water that fills our seas today. The timing couldn't be more perfect. Just as Earth cools enough to retain liquid water, the late heavy bombardment tapers off, leaving behind a wetter, richer world. Hydrothermal vents at the ocean floor become crucibles, mixing comet-derived organics with minerals and geothermal energy. Some scientists, like those behind the comet pond hypothesis, argue that shallow pools warmed by impacts could have been even more favorable, concentrating molecules through cycles of evaporation and rainfall, creating the perfect conditions for chemical complexity to emerge. Of course, not all impacts are equal. Too big and the energy sterilizes the planet. Too small and the organics burn up in the atmosphere. But get the Goldilocks zone just right, and you have a cosmic delivery system. One that doesn't just bring life's ingredients, but the energy and environments to assemble them. This might explain why life appeared so quickly once Earth settled down. Fossil evidence suggests microbes existed as early as 4.2 billion years ago, almost the moment the bombardment ended. Coincidence, or the sign of a universe that doesn't just create life, but actively seeds it? The next time you gaze at a comet streaking across the night sky, remember, you might be looking at more than a celestial spectacle. You could be witnessing a cosmic gardener scattering the seeds of existence across the stars. And if comets did it here, why not elsewhere? The universe, it seems, has a way of turning even the most violent collisions into acts of creation. Now let's zoom in on one of the strangest quirks in the chemistry of life, something so subtle. It's easy to overlook, yet so profound, it might hold the key to our cosmic origins. It's called chirality, or handedness, and it's a property that makes molecules non-superimposable mirror images of each other, like your left and right hands. They look identical, but no matter how you rotate them, they can't perfectly overlap. In the realm of amino acids, the building blocks of proteins, nearly all life on Earth uses just one form, left-handed. And here's the kicker: scientists have found the same bias in meteorites, suggesting this preference didn't start here. It might have come from space. Take a closer look at the molecular structure of an amino acid. At its core is a carbon atom bonded to 4 different groups: an amino group, a carboxyl group, a hydrogen atom, and a side chain. This arrangement creates 2 possible mirror image versions: left-handed, or L-amino acids, and right-handed, D-amino acids. In nature, both forms should appear equally. Yet when researchers analyze meteorites like the famed Murchison meteorite, which fell in Australia in 1969, they find an excess of L-amino acids. This isn't a fluke. The same bias shows up in multiple space rocks, and it lines up exactly with the preference seen in Earth's biology. So why does this matter? Because chirality isn't just a curiosity, it's a cosmic signature. If amino acids formed randomly on Earth, we'd expect equal amounts of left and right-handed versions. The fact that life uses almost exclusively L-amino acids hints that the bias was already present in the materials that seeded our planet. Some scientists think polarized light from neutron stars or the magnetic fields of interstellar clouds could have tipped the scales, selectively breaking down one form over the other. Others suggest the bias emerged in the icy grains of comets, where chemical reactions under ultraviolet light favor L-amino acids. The implications are staggering. If life's handedness was imprinted before Earth even formed, then the same preference could exist on other worlds. Imagine a distant planet bathed in the same starlight, seeded by the same comets. Its biology might mirror ours at the molecular level. Or consider the opposite. What if we found life with right-handed amino acids? That would be proof of a separate origin, a second genesis entirely. What's even more fascinating is how this molecular asymmetry shapes life itself. Enzymes, the workhorses of biology, are so finely tuned to interact with L-amino acids that introducing a right-handed version can disrupt their function entirely. This specificity suggests that life didn't just adapt to the bias it depended on it from the very beginning. The universe, it seems, handed us a template and life ran with it. So the next time you hear about a meteorite or comet carrying organic molecules, remember, it's not just about what's there, but how it's arranged. The answer to one of life's deepest mysteries, why we're built the way we are, might be written in the mirror image dance of molecules older than the stars. And if that's true, then our story isn't just Earth's story. It's written in the fabric of the cosmos itself, deep in the frozen heart of a comet, where temperatures hover just a few degrees above absolute zero, an invisible storm rages. Cosmic rays, high-energy particles flung across the galaxy by exploding stars, barrage the ice, slamming into molecules with enough force to tear them apart. At first glance, this seems like a death sentence for fragile organics, but here's the astonishing twist. That same destructive power might be the driving force behind life's molecular blueprints. Radiation doesn't just break things down, it rearranges them, sparking reactions that turn simple ices into complex chemistry. Picture a single water molecule locked in comet ice. When a cosmic ray strikes, it knocks atoms free, creating reactive fragments called radicals. These unstable pieces ricochet through the microscopic lattice, colliding with other molecules like billiard balls in slow motion. Some recombine into familiar compounds, hydrogen peroxide or formaldehyde. Others form amino acids like glycine, detected on Comet 67P by the Rosetta mission. Over millions of years, this particle ping-pong builds complexity, layer by layer, shielded from the vacuum by the comet's icy crust. Laboratory experiments back this up. Scientists at institutions like the University of Hawaii have recreated comet conditions in vacuum chambers, bombarding mock comet ice mixtures of water, methanol, and ammonia with proton beams mimicking cosmic rays. The results, organic compounds emerge, some with structures eerily similar to the building blocks of RNA. Even more compelling, the reaction rates match what we'd expect in real comets, suggesting this isn't just lab magic, it's a natural cosmic process. But radiation's role gets even stranger when we consider chirality, the handedness of molecules we discussed earlier. Polarized radiation, where light waves vibrate in a single plane, might explain why life favors left-handed amino acids. Experiments show that circularly polarized ultraviolet light, common around star-forming regions, selectively destroys one mirror image form over the other. Over eons, this could create the bias found in meteorites and life itself. Now, here's the paradox. While cosmic rays can synthesize life's ingredients, they also threaten to destroy them. Space is filled with ionizing radiation capable of shredding DNA in minutes. The key lies in balance, and comets strike it perfectly. Their outer layers absorb the worst of the radiation, while the interior remains a protected workshop where chemistry can unfold. Think of it like a bunker with thick walls, deadly outside but inside the perfect conditions for delicate work. This duality extends beyond comets. On early Earth, radiation from the sun and supernova may have similarly jump-started chemistry in tidal pools or underground aquifers. Some theories even suggest that without periodic radiation spikes, like nearby stellar explosions, life might not have emerged as quickly. It's a humbling thought. The same force that could sterilize a planet might also be the spark that ignites life in the first place. So next time you hear about the dangers of cosmic radiation, remember, it's not just a destroyer. It's a sculptor shaping the raw materials of existence in the most unexpected places. And if comets can harness that power, then perhaps life isn't the exception in the universe, but an inevitability, waiting patiently in the ice for its moment to awaken. For decades, the primordial soup theory has reigned supreme in explaining life's origins, a warm, watery cradle where simple molecules bubbled and bonded into complexity. Picture Earth 4 billion years ago, volcanic vents spewing minerals into shallow pools, lightning crackling through a methane-rich sky, and ultraviolet light bombarding the surface. In this cauldron of chemistry, the building blocks of life, amino acids, sugars, lipids slowly assembled, eventually forming the first self-replicating molecules. It's an elegant story, one backed by iconic experiments like Stanley Miller's 1953 electrical discharge test, which showed how lightning could spark organic molecules from simple gases. But here's the twist: what if that soup wasn't cooked solely on Earth? What if comets handed us the ingredients pre-packaged and ready to go before the stove even got hot? Enter the ultimate scientific showdown: hydrothermal vents versus comet delivery. On one side, vent enthusiasts point to Earth's deep sea geysers, where scorching, mineral-rich water meets cold ocean, creating gradients of heat and chemistry perfect for fostering life. These underwater towers, teeming with extremophiles today, could have been life's first laboratories, offering shelter from surface bombardments and a steady supply of energy. In their favor, the discovery of ancient microbial fossils near vent-like structures in Quebec, dating back to a staggering 3.8 billion years, almost as old as Earth itself. If life emerged that quickly, they argue, it must have had a head start, and vents provided the ideal incubator. But Panspermia advocates counter with a cosmic perspective. Comets, they note, aren't just water and dust, they're preloaded with organic molecules, some of which are hard to synthesize in Earth's early conditions. Take ribose, the sugar backbone of RNA. While vents can produce simple organics, ribose is notoriously fragile in heat, breaking down before it can accumulate. Yet, it's been found on comets preserved in their icy depths. Even more compelling, the amino acid bias we discussed earlier. If life's left-handed preference was already imprinted in space rocks, it suggests the recipe for life wasn't written here, it was delivered. Could both theories be true? Absolutely. Imagine comets as cosmic grocery trucks, dumping frozen organic supplies into Earth's early oceans. Hydrothermal vents then act as chefs, using geothermal energy to simmer those ingredients into something more complex. This hybrid model, dubbed comet-assisted abiogenesis, bridges the gap. Comets provide the raw materials, amino acids, sugars, phosphorus, while vents offer the stability and energy to organize them. It's not a competition, it's a collaboration. The debate gets even richer when we consider timing. The late heavy bombardment, that era of relentless comet strikes, overlaps neatly with the earliest evidence of life. Coincidence or cosmic delivery meeting planetary readiness? Some scientists, like astrobiologist Stephen Benner, propose that Earth's surface was simply too hostile early on, too hot, too radioactive for delicate biomolecules to survive. Only after comets helped cool the planet and deposit their cargo could vents take over, refining those gifts into life. Here's where the playful rivalry heats up. Vent purists joke that Panspermia just kicks the can down the road, moving life's origin from Earth to space without solving how it began. Comet fans retort that vents are too localized. How could life emerge in a few scattered hotspots and then spread globally so fast? The truth might lie in the middle. Maybe vents were the stage, but comets supplied the actors. Or perhaps life started multiple times in multiple places, with only the hardiest versions surviving. What's thrilling is how much we're still learning. Recent experiments show that comet-like ice exposed to vent conditions can produce even more complex molecules like peptides. Meanwhile, probes like NASA's upcoming Europa Clipper might find evidence of vent systems on icy moons potentially hosting life seeded by comets. The lines blur further with each discovery. So who wins the showdown? For now, it's a draw. Both theories push science forward, challenging us to think bigger. Whether life began in Earth's depths or the cosmic void, one thing's clear: the universe is far more inventive than we ever imagined. And the real winner, curiosity itself. High above the clouds, where the sky fades from blue to black, a team of scientists made a claim that sent shockwaves through the scientific community. Floating in Earth's stratosphere 25 miles up, beyond the reach of even the hardiest birds, they found something that shouldn't be there: microscopic particles resembling fossilized bacteria. Not just any bacteria, but organisms with structures unlike anything recorded in Earth's biosphere. The implications were staggering. If these weren't contaminants from our planet, could they be proof that life is still raining down on us from space? Let's rewind to 2001, when British astrobiologist Chandra Wickramasinghe, already a controversial figure for his Panspermia advocacy, launched a series of high-altitude balloon experiments. Strapping sterile collectors to weather balloons, his team sampled the stratosphere during meteor showers, times when cosmic dust would be most abundant. What they hauled back defied expectations. Under electron microscopes, the samples revealed tiny, cell-like structures less than a micrometer wide, some with intricate, segmented walls. A few even resembled diatoms, a type of algae. But here's the catch: these particles were too large to have been lifted from Earth's surface by normal atmospheric processes. Their presence at that altitude, Wickramasinghe argued, pointed to an extraterrestrial origin. Critics were quick to dismiss the findings. The scientific gold standard for proving alien life, after all, isn't just morphology, seeing shapes that look biological. It's chemistry. Without genetic material or isotopic signatures to confirm these particles weren't earthly contaminants, the claims remained speculative. Skeptics pointed to high-altitude winds that can carry terrestrial microbes farther than we once thought, or even volcanic eruptions that blast material into the stratosphere. In 2013, a similar study led by Milton Wainwright claimed to find a titanium-coated sphere oozing a gooey substance in stratospheric samples. The media dubbed it the alien seed, but peer reviews noted the sample could easily be industrial debris or a fungal spore coated in pollutants, yet the plot thickens. In 2020, independent researchers analyzing stratospheric dust from the Sahara discovered microorganisms with DNA that resisted amplification, a hint their genetic material might be too degraded or structurally unusual to match known earthly templates. Even more intriguing, some of these microbes survived exposure to UV levels that would obliterate most terrestrial bacteria. Proponents argue this hardiness mirrors what we'd expect from spacefaring organisms adapted to radiation. Of course, absence of evidence isn't evidence of absence. Just because we can't identify a microbe's origin doesn't automatically make it alien, but it does raise provocative questions. Zooming in under the microscope, the debate takes on a visual dimension. Footage from these studies shows particles with uncanny biological symmetry, hollow spheres resembling fungal spores, chain-like filaments reminiscent of cyanobacteria, and even rod-shaped structures that look eerily like fossilized extremophiles. Side-by-side comparisons with known Earth microbes reveal subtle differences. Unusual elemental compositions, exotic metal coatings, or isotopic ratios skewed toward what we'd expect from interstellar dust. One particularly striking example, a particle rich in vanadium and nickel metals abundant in meteorites but rare in Earth's lower atmosphere. So where does this leave us? The scientific community remains divided. Mainstream astrobiologists caution that extraordinary claims require extraordinary evidence, and so far, no study has definitively ruled out terrestrial contamination. But even skeptics admit the stratosphere is a bizarre frontier. It's a place where dust from the Sahara mingles with debris from comets, where bacteria blown upward by storms might encounter cosmic material falling downward. If Panspermia is real, this liminal zone, neither fully Earth nor fully space, might be where we find its fingerprints. Until we can sample pristine cometary material directly or detect living microbes in the void, the stratosphere offers our closest look at whether life, against all odds, might still be arriving from the stars. One thing's certain, the sky above us is far less empty than we ever imagined. If life really can hop between worlds aboard comets, lighting cosmic sparks wherever it lands, then where is everybody? This haunting question lies at the heart of Fermi's paradox, the unsettling gap between the universe's staggering scale and our utter isolation within it. With billions of potentially habitable planets in our galaxy alone, and mechanisms like Panspermia to spread life, the silence is deafening. One possible answer sends chills down the spine. Something stops life from advancing too far. Scientists call it the Great Filter, an invisible cosmic sieve that crushes civilizations before they can fill the stars. And comets, the very messengers we've been celebrating, might hold the key to understanding why. Think about Earth's own history. Life appeared almost as soon as the planet cooled, but complex organisms took billions of years to emerge. Then, just as intelligence flourished, we've teetered on the brink of self-destruction, through climate collapse, nuclear war, or runaway AI. What if this pattern isn't unique to us? What if comets deliver life seeds, but the universe conspires to keep them from growing too tall? The filter could lurk in the chemistry itself. Maybe most planets seeded by comets never develop stable oceans, or their amino acids never fold into proteins. Or perhaps when life does take hold, it inevitably consumes its own habitat, a tragic loop of bloom and bust written into biology's code. Here's where the paradox turns darker. If Panspermia is real and life spreads easily, then the filter isn't behind us, it's ahead. Every silent star system becomes a gravestone, marking civilizations that flamed out before they could leave their cradle. Comets might be both midwives and executioners, delivering life only for it to perish in cosmic adolescence. The icy plumes and organic-rich tails we've discovered. They could be echoes of countless failed experiments, a reminder that the universe is less a garden than a minefield. But there's another, more hopeful possibility. We're early. The universe is 13.8 billion years old, but it's still young by stellar standards. Future trillions of years will favor red dwarfs, stars that burn slowly and steadily. If life needs those stable eras to truly flourish, we might be among the first to even ask these questions. In that case, the silence isn't ominous, it's expectant. The comets carrying life's blueprints are still en route, and the great symphony of civilizations has barely begun. Either way, the lesson is humbling. Whether the filter lies in our past or future, the cosmos seems to balance creation and destruction with a razor's edge. Every comet streaking through the void carries not just the spark of life, but the weight of its fragility. So the next time you gaze at the stars, listen closely to that silence. It's either a warning or an invitation to outrun the shadow creeping behind us all. What if Earth wasn't just an accident, a random spark in the cosmic dark, but a deliberate project? This is the spine-tingling premise of directed panspermia, a theory so bold it came from one of science's greatest minds. Francis Crick, co-discoverer of DNA's double helix, wasn't content with the idea that life's complexity emerged by chance. In 1973, he dropped a bombshell paper suggesting an alternative. What if an advanced civilization sent life here intentionally? Imagine that, a biological blueprint carefully packed into a spacecraft or comet, launched across the void with Earth as its target. Crick's argument hinged on DNA's staggering complexity. Even the simplest living cell is a labyrinth of precise molecular machinery with thousands of interdependent parts. The odds of it assembling spontaneously, he argued, were like a tornado ripping through a junkyard and leaving behind a fully functioning jet engine. But if life's blueprint arrived pre-assembled, a genetic starter kit from the stars, suddenly the math made sense. He even speculated about the delivery method: dormant microbes, freeze-dried inside protective capsules, riding aboard meteorites or sleek probes designed to survive interstellar travel. Here's where it gets weirder. Crick wasn't alone in flirting with cosmic intervention. Legends like Fred Hoyle and Chandra Wickramasinghe saw comets as vectors for life, but their vision was passive, a natural spread of organisms drifting on celestial currents. Directed Panspermia, by contrast, implied intent. A civilization advanced enough to engineer life and aim it at promising planets wouldn't just be spreading biology, they'd be playing gardener on a galactic scale. Why? Maybe to terraform worlds for future colonization, maybe to preserve their genetic legacy, or, as some UFO enthusiasts suggest, maybe we are the colony, a living experiment monitored from afar. The UFO connection isn't coincidental. Stories of ancient astronauts and alien visitors often intertwine with directed panspermia, fueled by artifacts like the Nazca lines or the sudden explosion of human ingenuity during the Neolithic Revolution. Could these be clues left by our cosmic benefactors? Mainstream science dismisses such claims, but the underlying question remains haunting. If life was engineered, how would we know? Crick himself cautioned that evidence might be buried in our biology, perhaps a deliberate molecular signature, like a creator's watermark hidden in our genetic code. Skeptics, of course, have counter-arguments. The universe is 13.8 billion years old, plenty of time for improbable chemistry to become inevitable through sheer trial and error. And if aliens did seed Earth, where's the smoking gun? No alien probes, no unmistakable artifacts, just silence. But proponents counter that absence of evidence isn't evidence of absence. A civilization capable of directed panspermia would likely hide its involvement to avoid contaminating the experiment. After all, if you were running a cosmic lab, would you want your specimens aware they were being watched? The debate taps into something deeper than science. It's about our place in the universe. Are we alone? Are we accidents? Or are we part of someone else's story, written in DNA instead of stone? Whether Crick's theory holds water or not, it forces us to confront the awe-inspiring possibility that life might not just spread among the stars, it could be sent. And if that's true, the greatest discovery awaiting us might not be alien life, but the realization that we've been alien life all along. For centuries, we thought comets were unique to our solar system, ghostly travelers bound by the sun's gravity. Then, in 1984, astronomers studying the young star Beta Pictoris spotted something revolutionary: a vast disk of dust and gas, warped in ways that hinted at unseen bodies stirring the debris. The culprit, Exocomets, icy visitors streaking through another star's neighborhood, leaving faint chemical trails in their wake. Suddenly, our cosmic backyard felt a lot more crowded. Fast forward to today, and the evidence is overwhelming. Over 30 stars, from infant protostars to seasoned suns like Kappa Andromedae, show telltale signs of exocomet activity. How do we detect something so small and distant? The trick lies in starlight. As a comet plunges toward its star, ices vaporize, releasing gases like carbon monoxide and hydrogen cyanide. These create transient absorption lines in the star's spectrum, like fingerprints appearing and vanishing as the comet burns. Some systems, like HD 18265, even show periodic dips in brightness, suggesting swarms of comets eclipsing their star in perfect synchrony. But here's the jaw-dropper. Estimates suggest our galaxy alone could harbor a sextillion comets. That's a 1 followed by 21 zeros. If even a fraction carry organic molecules, the Milky Way might be a bustling highway for life's raw materials. Take the Exocomets orbiting Eta Corvi, a star eerily similar to our Sun's younger self. Spectroscopic analysis reveals they're rich in water vapor and complex hydrocarbons. a recipe eerily similar to the broth that likely seeded Earth. The math gets even wilder when we consider scale. The Oumuamua cloud, our solar system's icy reservoir, holds trillions of comets. Multiply that by the galaxy's 400 billion stars and the numbers defy comprehension. Factor in gravitational kicks from passing stars or rogue planets, events that routinely fling comets into interstellar space, and you've got a delivery system spanning light years. Simulations show a single ejected comet has a 10% chance of being captured by another star within a billion years. That's not geological time, that's a parcel service on cosmic speeds. Yet the real game-changer came in 2017 when Oumuamua swung through our solar system. This interstellar interloper proved comets do travel between stars. Then, in 2019, Borisov arrived, a confirmed exocomet leaking cyanogen gas, a compound found in our own comets. If two strangers passed through our neighborhood in just 2 years, how many more are out there ferrying cargo between unclaimed worlds? Critics argue most exocomets would sterilize organics with radiation over interstellar distances. But remember, comets aren't passive ice cubes. Their porous interiors act like radiation shields with layers of dust and organic crust protecting the goods within. Experiments at the University of Hawaii show amino acids trapped in ice can survive millions of years in deep space if buried just a few centimeters. Now imagine a comet the size of Hale-Bopp, its core a vault of frozen chemistry, drifting between stars until it smashes into a newborn planet's ocean. The implications are dizzying. If exocomets swarm the galaxy, then life's ingredients might be universal currency. A single system like Beta Pictoris, with its estimated 10 trillion comets, could have seeded 1,000 worlds by now. We're not just talking about lucky accidents. We're looking at a universe where life's building blocks are as common as stardust. And if that's true, then Earth's story might be playing out right now, on some distant world where another comet's payload is just beginning to stir. Let's crunch the numbers on a microbe's epic voyage through the void. Picture a bacterium huddled inside a comet's icy core, shielded from the worst of space's brutality, but still facing an unimaginable gauntlet of time and radiation. How long could it survive? The answer hinges on 3 brutal factors: cosmic rays, temperature, and the sheer length of interstellar travel. Start the clock at departure. Our microbe's home system fades into the distance as its icy ride gets hurled toward another star. Average comet speeds in interstellar space hover around 20 kilometers per second, though gravitational kicks can push them faster. At that pace, crossing the 4.3 light-years to Proxima Centauri, our nearest stellar neighbor, would take roughly 75,000 years. That's longer than all of recorded human history. But here's the twist: space is so empty that a comet could drift for millions of years before hitting another planetary system. Survival isn't about decades, it's about geological epochs. Radiation is the first threat. Cosmic rays, high-energy particles from supernova and black holes, rip through space at nearly light speed. On the surface, they'd shred DNA in hours, but comets aren't defenseless. Experiments show just 10 centimeters of ice can reduce radiation exposure 1,000-fold. Deeper inside, at a meter or more, doses drop to levels some Earth bacteria endure daily. Tardigrades, those microscopic tanks, have survived orbital radiation for years outside the ISS. What's the limit? Studies on Deinococcus radiodurans, a radiation-resistant bacterium, suggest it could persist for 8 million years in a comet's interior before cosmic rays finally erase its genetic code. Then there's the cold. Space averages minus 270 degrees Celsius, just 3 degrees above absolute zero. But cold isn't always deadly. For microbes in cryptobiosis, a dormant state where metabolism shuts down, freezing is a feature, not a bug. Antarctic bacteria have revived after 120,000 years in ice. Even more impressive, ancient Siberian permafrost has yielded viable microbes frozen for 2.5 million years. At interstellar temperatures, chemical reactions slow to a crawl, effectively pausing biological time. A microbe's molecular machinery might remain intact for eons, waiting for warmth to kickstart it back to life. The final hurdle, time itself. The longest dormant organism ever revived was a 250 million-year-old salt crystal bacterium, though that claim's debated. More conservatively, we know some spores can last tens of millions of years, but here's where comets offer a sneaky advantage. They're not just freezers, they're repair shops. When radiation does damage DNA, the extreme cold preserves broken strands until thawing allows repair enzymes to stitch them back together. It's like pausing a movie mid-scene and resuming centuries later without missing a beat. So let's tally the extremes. Shielded by a meter of ice, our hardy microbe could endure radiation for 8 million years and cold indefinitely. Even crossing 100 light-years, a fraction of the Milky Way, might take just 1.6 million years at higher speeds. That's well within survivable limits. Factor in comet collisions redistributing material between stars, and the numbers get wilder. Simulations suggest our solar system may have captured dozens of interstellar comets over its lifetime. If just one carried dormant life, the galaxy becomes less a desert and more a network of potential oases. The takeaway isn't just that microbes could survive these journeys, it's that the universe practically expects them to. From radiation shielding to deep freeze preservation, comets are nature's ark designed for billion-year voyages. And if life hopped here, who's to say it hasn't hopped elsewhere, threading the cosmos with invisible strands of biology? The next time you see a comet, remember, it might not just be a rock. It could be a ship carrying passengers we've only begun to imagine. Imagine a microbe no bigger than a speck of dust, encased in a tiny pocket of ice deep within a comet. Now picture that comet screaming through Earth's atmosphere at 50,000 kilometers per hour, its surface heating to thousands of degrees as friction turns the sky into a blistering inferno. It's a journey so violent, it seems impossible anything could survive, but nature has a way of defying expectations. The secret lies in two factors, shielding and speed. A comet's outer layers act like a sacrificial shield, absorbing the worst of the heat while the interior remains relatively cool. Experiments with heat-resistant bacteria like Bacillus subtilis show that even direct exposure to scorching temperatures isn't always a death sentence. In tests simulating atmospheric entry, these microbes survived when embedded just a few millimeters inside a mock comet material. The surface might vaporize, but deeper pockets stay intact, creating a temporary refuge. But heat isn't the only threat, there's also the crushing deceleration. When a comet fragment breaks apart, smaller pieces can slow down rapidly, spreading the energy of impact over more manageable forces. Researchers at the University of Kent tested this by firing microbial samples into water at hypervelocity speeds, mimicking a comet splashing into an ancient ocean. Astonishingly, up to 10% of the microbes survived, especially when cushioned by porous materials that absorbed the shock like a microscopic airbag. Then there's the comet's composition. Ice isn't just a coolant, it's a buffer. As the surface melts, it releases water vapor, creating a temporary insulating layer that deflects heat away from the core. This phenomenon, known as ablation cooling, is why some meteorites land cold to the touch despite their fiery descent. For microbes tucked inside, it's like riding a heat shield that constantly regenerates. The real-world evidence: look no further than Earth's extremophiles. Bacteria like Deinococcus radiodurans can endure radiation, vacuum, and extreme heat. Traits that would be overkill on Earth but perfect for a comet's journey. In 2009, scientists strapped samples of these hardy organisms to the exterior of the International Space Station. After 18 months exposed to raw space, some still revived when brought back to the lab. If they can handle that, a fiery plunge through the atmosphere might just be a bump in the road. Critics argue that even if microbes survive entry, the aftermath acidic oceans, scorched landscapes would finish them off. But here's the twist, comets don't always land in hellscapes. A gentle touchdown in a warm, shallow pond could be all it takes. Experiments with simulated comet impacts show that organic molecules not only survive but thrive when introduced to hydrothermal environments, where heat and minerals kickstart chemical reactions. It's less about surviving the crash and more about sticking the landing in the right neighborhood. So the next time you see a shooting star, consider this. That fleeting streak of light might not just be a burning rock. It could be a delivery van dropping off passengers that have waited millions of years for their new home. And if life could hitch a ride here, who's to say it hasn't done the same elsewhere, turning the cosmos into a silent, sprawling network of shared beginnings? Mars sits like a cosmic stepping stone between the asteroid belt and Earth, closer to the debris-rich outer solar system, battered by impacts long before our planet formed. If comets really did ferry life's ingredients across the solar system, Mars would have been their first logical stop. Picture the early solar system, a shooting gallery of icy wanderers with Mars squarely in the crosshairs. Its thinner atmosphere and lower gravity made it an easier target than Earth, absorbing countless comet strikes that could have deposited water and organics in staggering quantities. Evidence from NASA rovers confirms this: dried-up riverbeds, ancient lakebeds, and even traces of complex organic molecules in Martian soil. But here's the kicker: Mars cooled faster than Earth, meaning it might have been habitable before our planet was. If life had a head start there, could fragments of it have hitchhiked to Earth on debris ejected by later impacts? Consider the timeline. Around 4 billion years ago, during the late heavy bombardment, both planets were pummeled by comets, but Mars, being smaller, lost its protective magnetic field sooner. Solar radiation stripped away its atmosphere, turning lakes to dust. Yet beneath the surface, microbes could have persisted, sheltered in subsurface aquifers or deep rock fractures. Fast forward to today, and we've found methane spikes in Mars' atmosphere, a gas often produced by living organisms on Earth. Even more intriguing, the Martian meteorite LH84001, discovered in Antarctica, contains tiny carbonate globules and structures some scientists argue resemble fossilized bacteria. The debate rages, but the possibility remains. If life existed on Mars, it might share a common ancestor with Earth's earliest organisms, carried here by a comet-sparked diaspora. This isn't just about microbes, it's about architecture. If Martian life used the same molecular toolbox as Earth's left-handed amino acids, DNA-like polymers, it would hint at a shared origin. Conversely, finding different biochemistry would be even more revolutionary proof that life arose independently, making the universe a factory of biological innovation. NASA Perseverance rover is now drilling samples that could hold answers, with a future mission slated to bring them home. Imagine unearthing a microbe on Mars with genetic material eerily similar to Earth's extremophiles. The implications would ripple outward, not just that life spread, but that it prefers to spread using comets as its delivery network. So while we scour Mars for signs of life, we're also hunting for our own cosmic genealogy. Every crater there might be a chapter in a story that began with icy visitors from the outer solar system and ended with us, beneath the cracked, icy shells of Europa and Enceladus, two of our solar system's most mysterious moons. Entire oceans slosh in perpetual darkness, vast liquid water reserves hidden under miles of frozen crust. These aren't just any oceans, they're warm, salty, and rich in the very chemicals that make life possible here on Earth. And here's the electrifying part: those life-giving ingredients might not have originated on these moons at all. They could have been delivered by comets, the same icy messengers that might have seeded our own planet. Start with Europa, Jupiter's enigmatic moon. Its surface is a labyrinth of fractures and ridges, crisscrossed by reddish streaks scientists call chaos terrain. These markings hint at a subsurface ocean kept liquid by tidal forces, Jupiter's immense gravity flexing Europa's core, generating heat through friction. But what's really staggering is what NASA Galileo spacecraft detected. Plumes of water vapor erupting from these cracks, shooting hundreds of miles into space. When the James Webb Space Telescope analyzed these plumes in 2022, it found not just water, but carbon dioxide and organic molecules swirling in the spray. These are the same compounds comets carry in abundance. Coincidence or evidence that Europa's ocean is laced with comet-delivered chemistry? Now zoom to Enceladus, Saturn's glittering snowball of a moon. Here, geysers near the South Pole blast water ice and organic compounds into space at over 800 miles per hour, so much material that it feeds Saturn's faint E-ring. When the Cassini probe dove through these plumes in 2015, its mass spectrometer hit the jackpot, a buffet of complex molecules including methane, propane, and even hints of amino acids. But the real shocker was hydrogen gas, a sign of hydrothermal vents on the seafloor below, where mineral-rich water might be cooking organics into ever more complex forms. This is where the comet connection gets spine-tingling. Both moons are too small to have formed with these chemicals on their own. Their organics had to come from elsewhere, and comets are prime suspects. Imagine a primordial impact back when the solar system was young. A comet the size of a city slams into Europa, its icy shell still forming. The collision melts through the crust, dumping water, ammonia, and probiotic molecules straight into the subsurface ocean. On Enceladus, the process might have been gentler, a dusting of comet fragments over millennia, their organics seeping through cracks opened by tidal heating. The implications are staggering. If comets stocked these oceans with life's raw materials and hydrothermal vents provided the energy to rearrange them, we're not just looking at watery graveyards. We're looking at incubators. Laboratory experiments show that in Enceladus-like conditions, alkaline water, silica-rich minerals, and a dash of formaldehyde can produce amino acids in weeks. Europa's more acidic ocean might favor different chemistry, but the principle holds. Given the right ingredients and enough time, complexity emerges. And then there's the snow. Every time Enceladus erupts, it launches ice grains into space, some escaping Saturn's gravity to drift among the stars. These aren't just flecks of frozen water. They're microscopic time capsules, potentially carrying organic material from the moon's hidden sea. Future missions like NASA Europa Clipper or a proposed Enceladus Life Finder could fly through these plumes, tasting them for signs of molecular complexity we'd recognize as biology. Critics argue that without direct evidence of life, this is all speculation. But consider the alternative. If comets delivered life's building blocks to Earth, why not here? These moons have been tucked away from solar radiation, their oceans stable for billions of years, far longer than it took life to arise on our planet. They're not just frozen relics, they're test tubes holding experiments that began when the solar system was in its infancy. So as we peer into the plumes of Enceladus or map the chaos terrain of Europa, we're not just exploring moons. We're reading a cosmic recipe book, one where comets might have written the first instructions. And if life ever stirs in those dark, alien seas, its origins could trace back to the same icy travelers that might have sparked our own existence. The universe, it seems, has a habit of leaving its fingerprints everywhere, even in the deepest, darkest waters. Deep within the icy heart of a comet, where temperatures plunge hundreds of degrees below zero and cosmic radiation weaves through frozen cracks, something extraordinary might be happening, a slow-motion chemical dance, arranging atoms into the very molecules that could spark life itself. The RNA world hypothesis, long a cornerstone of origins of life research, paints a picture of Earth's early oceans teeming with self-replicating RNA strands, the precursors to all modern biology. But what if that story didn't begin here? What if the first strands of RNA didn't simmer in tidal pools but instead arrived fully formed, nestled inside comets like cosmic care packages? Think about RNA's unique qualifications. Unlike DNA, which needs proteins to replicate, RNA can act as both blueprint and builder, storing genetic information and catalyzing chemical reactions. It's the ultimate multi-tool, capable of copying itself under the right conditions. Scientists have even synthesized RNA strands in labs that evolve, compete, and grow more complex over generations. Now imagine that process unfolding not in a sterile beaker, but in the fractured, icy matrix of a comet's interior. Here's where the cosmic and terrestrial theories collide. Experiments show that comet-like ice, mixtures of water, ammonia, and cyanide exposed to ultraviolet light or cosmic rays can produce nucleobases like uracil and cytosine, key components of RNA. Even more compelling, when these icy mixtures are subjected to the gentle warming of a young star, they form ribose, the sugar backbone of RNA. Comets aren't just passive carriers, they're dynamic chemistry labs with temperature swings and radiation pulses driving reactions that Earth's milder environment might struggle to replicate. Consider this scenario. A comet drifts through the interstellar void, its surface pelted by cosmic rays that trigger molecule-building reactions in its icy layers. Over millennia, simple compounds link into nucleobases, which then attach to ribose molecules forming in the comet's warmer pockets. Eventually, these components assemble into short RNA strands, sheltered from destructive radiation by the comet's bulk. Then, during the late heavy bombardment, the comet smashes into Earth, splashing its cargo into warm ponds where the RNA strands, now bathed in liquid water and minerals, begin replicating. The beauty of this merger between Panspermia and the RNA world is how it solves two puzzles at once. RNA's fragility on early Earth, vulnerable to UV light and hydrolysis, becomes less problematic if it arrives pre-packaged in protective ice. Meanwhile, the improbable odds of RNA forming de novo in Earth's oceans shrink if comets deliver partially assembled ingredients. Critics argue that even comet-borne RNA would struggle to survive atmospheric entry or the chaos of impact. But recent studies reveal surprising resilience. When RNA is trapped in clay-like minerals, exactly the kind found in comet dust, it can withstand temperatures up to 400 degrees Celsius. And in microgravity experiments aboard the International Space Station, RNA strands folded correctly despite harsh radiation, suggesting space might aid molecular complexity rather than destroy it. The implications ripple far beyond Earth. If comets could seed one planet with RNA, why not others? Europa's hidden ocean or Saturn's moon Enceladus, with their organic-rich plumes, might host similar experiments in progress. The universe, it seems, isn't just a place where life might emerge. It's a place where the tools for life are actively assembled and delivered, one icy traveler at a time. So the next time you hear about a comet streaking through the solar system, don't just admire its brilliance. Consider the possibility that within its frozen core, molecules are quietly arranging themselves into something far grander, a blueprint not just for life on Earth but for life everywhere. The RNA world might not be a local phenomenon. It could be a cosmic imperative written in the chemistry of the stars. The moment a spacecraft drills into an alien world or scoops up a sample of comet dust, a silent race begins not just to uncover secrets but to outrun contamination. Every discovery of organic material in space comes shadowed by the same gnawing question: are we looking at extraterrestrial life or just traces of our own? This isn't just scientific nitpicking, it's a fundamental hurdle that could make or break humanity's search for our cosmic kin. Take the infamous case of the Viking landers in 1976. When NASA twin probes touched down on Mars, their life detection experiments returned ambiguous results, chemical reactions that could have been biological, but also matched known non-living processes. Years later, some scientists argued the organic molecules detected weren't Martian at all, but cleaning solvents from Earth that survived sterilization. The lesson: even the most rigorous protocols can leave blind spots. Fast forward to today, and missions like NASA's Perseverance rover tackle this challenge with obsessive precision. Its sample tubes, destined to return to Earth in the 2030s, were baked at 300 degrees Celsius and sealed in ultra-clean facilities, with scientists swabbing surfaces constantly to monitor for stray DNA. Yet contamination risks aren't just about Earth life hitching a ride out. They also threaten samples coming back. When Japan's Hayabusa 2 brought asteroid grains to Earth in 2020, the capsule plunged into Australia's outback, a relatively sterile environment, but future missions targeting icy moons like Enceladus will need to guard against Earth organisms infiltrating samples during transit. One proposed solution: break the chain of contact. Future landers might transfer samples via robotic arms inside sterile glove boxes, never directly touching spacecraft surfaces exposed to space radiation. The stakes skyrocket when considering false positives. In 2010, researchers analyzing Antarctic meteorites found bacteria-like structures, sparking headlines about Martian fossils until genetic analysis revealed terrestrial contamination. Conversely, overly strict sterilization could destroy delicate extraterrestrial organics. The balance is razor-thin. Too lax and every microbe becomes an alien; too harsh and we might erase the very evidence we seek. Enter next-gen solutions. NASA Europa Clipper, launching soon, will map the Moon's ice shell using spectrometers tuned to detect organic molecules without physical contact. Meanwhile, private ventures like Breakthrough Starshot propose laser-driven microprobes that could sample distant worlds without risking contamination at all. The dream: a universal biosignature framework, chemical or structural patterns so distinct they couldn't possibly be terrestrial. Think of it as a cosmic fingerprint, maybe a ratio of carbon isotopes found only in deep space, or an amino acid configuration never seen on Earth. This isn't just about avoiding embarrassment, it's about rewriting the rules of discovery. If we one day hold proof of alien life, we'll need certainty beyond doubt. Because in this grand cosmic detective story, the greatest mystery isn't just finding the clues, but knowing they're real. The race to unlock a comet's deepest secrets is heating up, and the next generation of missions is armed with tools straight out of a sci-fi novel. Leading the charge is the European Space Agency's Comet Interceptor, a pioneering spacecraft with a daring plan to lurk in deep space, lying in wait for an interstellar visitor like Oumuamua to barrel through our solar system. Unlike past missions that targeted known comets, the Interceptor will launch before its quarry is even discovered, parked at Lagrange Point 2, a gravitational sweet spot 1 million miles from Earth. Once a promising comet or interstellar object is spotted, the probe will kick into high gear, deploying 3 smaller craft for a coordinated assault. One will analyze the comet's nucleus, another its gassy coma, while the third maps magnetic fields and plasma. The goal: catch pristine material untouched by the sun's heat, preserving the raw chemistry that might hold clues to life's cosmic journey. Meanwhile, NASA's Dragonfly mission takes a radically different approach, not chasing comets but landing on a world they might have seeded, Saturn's moon Titan. This nuclear-powered rotorcraft, resembling a large drone, will hop across Titan's dunes and methane lakes, sampling organic-rich sediment for signs of prebiotic chemistry. While not a comet mission per se, Dragonfly's findings could reveal how comet-delivered molecules evolve in alien environments. Its mass spectrometer, laser spectrometer, and gamma-ray detector will scan for amino acids, lipids, and other compounds, the same toolkit that could one day analyze a comet's interior. Picture this: Dragonfly's rotors churning through Titan's haze, its drills biting into soil laced with comet-borne organics, while back in deep space, the Comet Interceptor dissects a pristine, icy wanderer. Together, they form a pincer movement attacking the Panspermia puzzle from two fronts. What sets these missions apart isn't just technology, it's timing. The Comet Interceptor aims to intercept an object fresh from interstellar space, untouched by billions of years of solar heating. That's critical because heat alters organic molecules, erasing their original signatures. Dragonfly, on the other hand, lands in a frozen time capsule. Titan's -180 degrees Celsius surface preserves organics like a cosmic freezer, offering a snapshot of how comet-derived chemistry behaves over millennia. The synergy is electrifying. One mission captures the delivery van, the other examines the unpacked goods, but the real game changer lies in their biosignature detection. The Comet Interceptor's manifest instrument can differentiate between left and right-handed amino acids, a potential smoking gun for life's cosmic origins. If it finds the same bias we see in Earth's biology, it hints at a universal preference imprinted before planets formed. Dragonfly's Draw-a-Mess spectrometer goes further, hunting for molecular patterns that resemble known biological systems. Neither is designed to find life directly, but both could uncover the scaffolding life might build upon. Critics argue these missions are long shots, space is vast, and pristine interstellar comets are rare. Yet the payoff could redefine our place in the universe. Imagine the interceptor catching a comet rich in complex organics, their chirality matching Earth. Or Dragonfly discovering metabolic precursors in Titan's dunes, their structure echoing comet chemistry. Suddenly, Panspermia shifts from fringe theory to frontline science, and the icy bodies streaking through our skies become more than spectacles. They're chapters in a story spanning stars. The clock is ticking. Comet Interceptor launches in 2029, Dragonfly in 2034. When their data streams in, we won't just be studying comets or moons. We'll be reading the universe's recipe book, one where the ingredients for life might be written in the ice of ancient travelers, and if those recipes match our own. The cosmos suddenly feels a lot less lonely and a lot more like home. Inside a high-security laboratory at NASA Ames Research Center, scientists are recreating the birth of the solar system. Not with telescopes or computer models, but with a machine that looks like a cross between a deep freezer and a futuristic espresso maker. This is the Cosmic Ice Laboratory, where researchers take simple molecules like water, ammonia, and methane, the same ingredients found in comets, and subject them to the brutal conditions of deep space. The goal, to see if the chaotic dance of radiation and ice can spark the chemistry that leads to life. The process begins with a vacuum chamber chilled to -260 degrees Celsius, just a whisper above absolute zero. Inside, gases are frozen onto a metallic finger, forming a thin layer of ice no thicker than a sheet of paper. Then comes the cosmic ambush. A beam of high-energy protons mimics the barrage of radiation that real comets endure as they drift between stars. What happens next is pure alchemy. The radiation shatters simple molecules, creating a zoo of reactive fragments that collide and recombine into more complex structures, amino acids like glycine, sugars like ribose, even nucleobases, the letters of our genetic code. But the real magic happens when scientists warm the ice. As temperatures rise, mimicking a comet's approach to the sun, the frozen matrix begins to crackle with activity. Molecules that formed separately now link together, like pieces of a puzzle assembling themselves. Infrared spectrometers capture the transformation in real time, revealing bonds forming between carbon and nitrogen atoms, the skeletal framework of life's essential molecules. One experiment in 2018 produced uracil, a key component of RNA, from nothing more than pyrimidine trapped in ice and zapped with UV light. It's proof that the universe doesn't need a lab coat to play chemist. The stakes of this research go beyond theory. When the Rosetta mission detected glycine on Comet 67P, it wasn't just a lucky find, it was a validation of decades of lab work. Now, scientists are pushing further, simulating not just ingredients but entire environments. At the University of Hawaii, researchers built a comet impact simulator, firing projectiles into ice laced with organic compounds at speeds topping 20,000 miles per hour. The result, under the right conditions, impacts don't destroy delicate molecules, they forge them. The shock waves act like a cosmic pressure cooker, squeezing simple ices into complex chains. Yet the most haunting discovery isn't what these experiments create, but how easy it seems to be. In 2021, a team at the University of Sherbrooke in Canada left a mixture of ammonia, methanol, and cyanide in a freezer for months with no added radiation. When they checked the samples, they found adenine, one of DNA's building blocks, had formed spontaneously. The implications are staggering. If life's raw materials assemble this readily in the frozen dark, then comets aren't just carriers. They're factories endlessly churning out the pieces of life wherever they roam. So next time you hear about a comet streaking through the solar system, remember, hidden in its icy heart, molecules might be quietly arranging themselves into something far grander. And in labs across the planet, scientists are racing to decode that cosmic recipe, one glowing ice sample at a time. Imagine a spacecraft hurtling toward a distant exoplanet, its payload not scientific instruments, but living organisms, microbes, algae, or even tardigrades bred to survive the harshness of space and awaken on a new world. This isn't science fiction. It's a real proposal gaining traction among some scientists, the idea that humanity should actively seed life beyond Earth. Proponents argue it's our cosmic duty, a way to ensure life's survival if disaster strikes our planet. But critics fire back. What right do we have to play God with ecosystems we don't understand? The debate cuts to the heart of our role in the universe. Are we stewards of life's spread or reckless interlopers in a delicate cosmic balance? On one side, advocates like astrobiologist Michael Mortner make a compelling case for directed panspermia. His vision: launch hardy, radiation-resistant bacteria toward exoplanets with Earth-like conditions, jump-starting evolution where nature hasn't yet taken root. The logic is seductive. Life on Earth is fragile, vulnerable to asteroid impacts, supervolcanoes, or our own self-destruction. By sprinkling life across the stars, we'd create backups, ensuring biology persists even if we don't. Some go further, suggesting we're simply continuing a process that may have begun billions of years ago. If comets seeded Earth, why shouldn't we pay it forward? Yet the risks loom large. Contamination is the nightmare scenario. Imagine a probe crashing into Europa's subsurface ocean, only for scientists to later discover native life, now outcompeted or poisoned by our imported microbes. The Viking landers were scrubbed with obsessive care to avoid this. Modern guidelines for planetary protection treat alien environments like sterile hospital rooms. Critics point to Earth's own history of invasive species, cane toads in Australia, zebra mussels in the Great Lakes as cautionary tales. If a single introduced species can ravage an ecosystem on Earth, what havoc might Earth organisms wreak on a world where life, if it exists, has evolved in isolation for eons? The ethical lines blur further when we consider unintended consequences. Even if a target world seems barren, we might disrupt probiotic chemistry, the slow simmer of molecules that could have eventually sparked life independently. By introducing organisms too soon, we could overwrite a planet's natural trajectory, like scribbling over the first page of an unwritten book. Some ethicists frame this as a form of cosmic vandalism, assuming alien life should resemble Earth's rather than allowing the universe to experiment with entirely novel biologies. Yet a middle path emerges. What if we focus on stepping stone worlds, places so hostile that life is unlikely, but where extremophiles could survive? Mars' subsurface or Venus' upper clouds might fit this bill. By establishing microbial footholds there, we'd test life's resilience without threatening potential native ecosystems. Others propose a strict look but don't touch rule, sending life only to planets we're certain are sterile, or waiting until we can survey them up close with AI probes. The Breakthrough Starshot initiative, aiming to send tiny probes to Alpha Centauri, offers a template, ultra-lightweight, non-contaminating spacecraft that could scout first, seed later. The philosophical stakes are just as dizzying. If we decide to spread life, we're making a statement about intelligence's role in the cosmos, that conscious beings should act as shepherds, guiding evolution where chance hasn't. It's a vision both humbling and audacious. We, a young species on a pale blue dot, taking up the mantle of life's guardians, but with that power comes peril. One misstep and we might not just fail, we could erase possibilities the universe spent billions of years preparing. The question isn't just whether we can. It's whether we should, and for that, there's no easy answer, only the stars, silent and waiting. From the discovery of amino acids on Comet 67P to the resilience of tardigrades surviving the vacuum of space, the evidence for comets as life's cosmic couriers is mounting. These icy wanderers aren't just celestial debris, they're time capsules packed with the raw ingredients of biology. Glycine dancing in comet tails, ribose sugars tucked beneath icy crusts, and even phosphorus, the backbone of DNA, detected in their shimmering comas. Laboratory experiments confirm what space missions like Rosetta and Deep Impact have shown: comets are chemical factories, where radiation and extreme cold forge life's building blocks from simple ices. And let's not forget the extremophiles, those microscopic survivors thriving in Earth's harshest corners, proving life can endure conditions once thought impossible. If a bacterium can weather interstellar radiation or a comet impact, why couldn't life hitch a ride across the stars? But the most tantalizing clues lie in the details, the left-handed bias of amino acids found in meteorites, mirroring Earth's biology, or the way comets deliver water and organics in one apocalyptic package. These aren't random accidents, they're patterns, hints that the universe might favor life spread using comets as its messengers. Even the gaps in our knowledge, like how RNA-like molecules could survive interstellar journeys, are shrinking thanks to experiments showing how cometary ice shields delicate chemistry from destruction. So here's the thought we'll leave you with. If comets seeded Earth, then every tree, every creature, every human is part of a lineage stretching beyond our planet, a family tree rooted in the stars. The next time you see a comet streak across the sky, consider this. You might be looking at a distant cousin, a fragment of the same cosmic ancestry that brought life to our world. What do you think? Are we the children of interstellar seeds, or is the truth still waiting to be uncovered? Drop your wildest theories in the comments below. Let's keep the conversation as boundless as the cosmos itself.